Okay, let's start. So, hi everybody. Welcome to this week's Indian Machine Learning Reading Group. Today's speaker is Sarah Masud. Sarah is a fifth-year doctoral student at the Laboratory for Computational Social Systems at IIIT Delhi. She works in the broad area of social computing, and her work mainly revolves around hate speech detection and diffusion on the web. She has been a recipient of both the Prime Minister's Research Fellowship as well as the Google PhD Fellowship. And apart from research, she's also volunteered with anitab.org and a reviewer with the Journal of Open Source Software. Sarah, on to you.
Thank you. I hope you guys can hear me. So we'll start the presentation now. I hope the slides are visible.
Yes.
Okay, cool. So hi everyone, and thank you for the introduction. So yeah, I'll be talking about one of our works in the area of analyzing hate speech detection systems. So what happens is that when we talk about trying to develop or even not even develop new models, but just fine tune existing systems for hate speech detections, we pretty much follow the hyperparameter tuning setting or the general setting what has been used in the NLP pipeline, and we wanted to see how much of that is effective in terms of hate speech detection as a whole, and if there are any patterns or policies that can be generalized. Of course, given hate speech is subjective, we end up with a broad conclusion that it's very difficult to give like a fix solution that will fit the current as well as the future set of problems as well as the data sets that we have. But still, we wanted to see what kind of interesting patterns emerge, and if there are anything with from this that can be broadly applied to the future research in NLP, and that what became the paper that it is. So from the title, I'll clarify that PLMs mean pre-trained language models. We are talking about the family of model that is BERT, Roberta, and variants of those, and we will not be talking about GPT-3 or beyond LLMs. So we'll be focusing this on fine-tuning BERT and BERT-based variants. So why do we want to study this? As I was saying that it's difficult to come up with a generalized pattern within hate speech literature, because hate speech as a definition is not well defined within the social science as well as the NLP community, which means that like other glue benchmark, you don't like have a benchmark for hate speech, which means that every new event, every new instance, year, geography, you have different hate speech data sets. Now, given that you have so many hate speech data sets, how do you go about analyzing the information in them? How do you go about setting some patterns or practices that can be, best followed within the hate speech community, so that the overall computation required can be reduced, or at least if not reduced, then can we narrow down the set of things that we should and should not do? Like at least give a broad perspective on what's out there. So that is, as I said, what motivated us, and we study this in terms of 5 research questions that are divided into 2 main setups. One is coming from the pre-training background. So what kind of pre-training data, what kind of checkpoints impact the downstream fine-tuning, and the other is the impact of the fine-tuning strategies itself, which includes type of classifier, head, type of layer freezing, unfreezing, setting trainable, and that sort of thing. So pre-training and fine-tuning setups, basic, and of course the end result is fine-tuning on the downstream task for hate speech detection. And here we use 7 English hate speech data sets, and we, for the ease of the experiment, we binarized them into hate and non-hate, because some of them have classes beyond hate and non-hate. So for easier analysis and comparison, we binarized all the data sets, and currently the work focuses on English data sets, because 3 of our experiments can only be run on in models that are available for English, and I'll show you why that is. And of course, as I said, we try bird-based variants, and we try different classification head. So a simple classification head would be what we normally use, is a linear layer followed by a softmax. Medium would be two layers. Complex would be, apart from two layers, you can add dropout layers. You can make the classification head even more complex. Maybe in future you can add a RNN layer or an LSTM layer on top of this. So you can keep on increasing complexity. And of course, because we wanted that the results to reduce the confounding variables in the results, we made sure that the experiments that we run, each of the experiment is run on 3 different set of seeds for the classification head. So when the classification head is initialized, we initialize them with 3 random seeds, and if the results are not shown seed wise, then they are average across 3 seeds. So these are the 7 data sets that we use, and these are the 5 models that we use. And as I was saying that initially their label, so this is the binarized version, but initially their label may or may not have binary data sets. And as you can see, most of them are obtained from Twitter, and most of the data collection happens before, say, your 2021. Like there's just one toxygen, but toxygen itself is generated by GPT-3. So again, whatever training that GPT-3 at that point might have had, it cannot be going beyond 2021, 2022. So most of the data sets that we have are curated from that timeline. And in fact, up till OLED, you can say that this pretty much covers most of what the PLMs have. So in terms of PLM, you see that BERT or MBERT models that we largely talk about, they are curated in 2018. The more later versions that we use in our use case, like HeadBERT or BERT, are 2020. So that's pretty much kind of the timeline where we see that there is an overlap between datasets and PLMs, and these datasets also come prior to the PLMs themselves. So just a quick overview when I'll be talking about other BERT variants. So in terms of BERT and MBERT, we know that MBERT is an extension of BERT, where they included 104 languages, and they applied the MLP and next sentence prediction similar to how they did in BERT. Then we also have some domain specific models like HeadBERT and BERT. So what we mean by domain specificity is that in our usual when you are usually training your language models, whether it is PLM or LLMs, what happens is that you have this whole corpus of data from the web. Say all of the Wikipedia in English is your data corpus. So that's a huge corpus, and then you perform your usual MLP and NSP, and then whatever model you get, it becomes a large scale model, but it is general model, so it can work for a number of tasks. But what if you only wanted a model for, say, medical data? Now, of course, curating such a vast amount of medical data is not possible. But what we are assuming is that this large model must have learned some information about medicine, and we can extend upon that by using a limited set of documents about medicine. So it could be patient's PDF, it could be doctor's notes, or other like PubMed data, and we can have a medium-sized corpus, again unlabeled. So both the initial PLM data sets are unlabeled. And what we do is that we take our language model that was learned in the generalized manner. We use the weights of that model as our initial weights, and we perform another round of pre-training. But this pre-training is done only on the specific domain dataset, and then of course the model that you get becomes your domain specific model. So in our case, the 2 domain specific models that we will be covering is BERT and HeadBERT. So BERT, what they did, they perform MLM on around 800 million tweets. And so basically the aim is to learn the linguistic features of how people post or write on Twitter. And HateBot was trained on almost 1 million posts from Reddit that were potentially offensive. Again, this offense was not like a labeling that they did, but they said that, okay, there are certain subreddits. If you know about Reddit, the concept is that you have certain groups like Reddit subreddit groups, and some of these groups themselves are more controversial. So a group about abortion or feminism will receive a stronger language than say about which like technology to use for your camera. So things like this. So they figured out, okay, there are certain subreddits that can be potentially more offensive. Let's collect the post from there, and then they performed MLM. So this was an interesting result that the authors shared on their paper, that when you have a simple masking like women are a dash, and the BERT model, for the BERT model, these are the top 3 terms that come up. But in the hate BERT model, you can see that the terms are tending towards being offensive. So the objective of hate BERT being able to capture the domain of how offensive things are, and how people share offensive information, that's kind of getting captured here. So these are the two domain specific models that we'll be using. Now we're talking about the first set of experiments, which is analysis on the pre-trained backbone. So the first question is just it's more of like trying to develop insights, and it was less about trying to develop the insights and more about establishing the status quo. So we know in deep learning that random seeds can lead to variation in performance, and we just wanted to like uh, justify this and satisfy this for our use case as well. So what we did was we took help from 25 checkpoints of BERT model that has been released in a paper, where what they did was that everything in the pre-training of the BERT is same, but what the authors did, they initialized a seed value, and that seed value was used to shuffle the training data, as well as the same seed was used to initialize the weight of the initial like pre-trained LLM before the initial weights of the model that will be trained. So basically they used 25 random numbers, like from 1 to 3 to 25, and they released 25 different variants of BERT, where the only difference is that they are pre-trained with different checkpoint. So we picked this BERT model. It's only for English, and we took 5 seeds, 0, 5, 10, 15, 20, and then for this particular seed, so let's say seed 0, we picked the pre-trained checkpoint that the authors provided for this, and for the say checkpoint 0, checkpoint 5, checkpoint 10 are like the 5 different variants of BERT, which only differ in how they were initialized and nothing else. So we took these 5 checkpoints, and then we fine-tuned our data set on that. And here we kept the fine-tuned, sorry, the pre-trained BERT as frozen, because we again wanted to reduce the number of confounding variables that can impact the final result. And fine-tuning was done for like 2 epochs, because most of these data sets are not that huge in size. So 2 to 3 epochs was sufficient for most of these. And again, for each combination of the data set and classification head, we tried to see the results. So of course, as expected, using a variation of your MLP seed, which is a classification head seed, and the pre-training seed, you see that there's a difference in performance. So within the same data set, the minimum and maximum F1 that can be obtained varies depending on the seed values that are employed. And for most of them, this difference was significant. So it means that, of course, the insight is that, of course, as expected, there is definitely a variation. And we because we kept our pre-trained model frozen, so the variation caused by the classification head was more than that caused by the change in the pre-training seed that was like expected. And of course, the takeaway here is that whenever we talk about sharing
Sarah, you got muted.
hi, am I audible again?
Yes.
Okay. Yeah. So as I was saying that the main takeaway for the hate speech community as well as for every one within the deep learning community is that we should always report our results that are average across multiple seasons. If you're performing fine tuning activity or any like including any form of like MLP layer or any layer that requires weight initialization within your system, it's always advised to run it on multiple seats, and this is what we found. It's like the pretty standard thing. So but this was kind of trying to verify that okay, some things within fine tuning of hate speech is in line with existing NLP research. Then based on the previous result, we saw that okay, pre-trained checkpoint initialization is creating a variation. What about the checkpoint itself in terms of the epoch when it is trained? So this is another English Roberta model that was released, where what the authors did was, so they trained the Roberta English model exactly as it is given in the Roberta paper, but what they did was that for each epoch of the model that was getting pre-trained, they saved the checkpoint. So the final model was trained for 84 epochs, and at each epoch the authors released a checkpoint. So we have 84 intermediate pre-training checkpoints, and then we take one checkpoint at a time. We keep that checkpoint frozen, and then we again fine tune on different data sets and different your classification head combination. So again this was in English, so we had to go with only English only models here, and sorry, English only data sets here. And here again we saw a variation based on the checkpoint that we picked. So the initial hypothesis that one would have is that yeah, what will happen is that some after some checkpoints, let's say checkpoint 30, you will see that the hate speech performance like keeps on increasing, and then beyond that it kind of plateaus. Like beyond like it has, by the time it reaches certain checkpoint, it has learned sufficient information about hatefulness that exists within the corpus that it is pre-trained on. So that's the pretty standard hypothesis that you have, like how in image learning and convolution you know that okay, each convolution layer or each after each training of the layer, you will see that the latent space feature existence becomes more and more prominent, and then it kind of remains the same, and more training doesn't help. But what we found here was that the earlier checkpoints were somehow giving the highest performance. So here, this is an example on Davidson, but I'll show this for all the other data sets as well, because it's a very interesting result that we found, that the checkpoint that was released after the third or the second epoch of the pre-training, that checkpoint was giving the highest performance. So you do see that there is variation across checkpoints. So at different learning epoch, the model is learning different things about the latent information in hate. So this learning that I'm talking about, it's in the pre-training stage. But when you take that specific pre-trained epoch model and apply it to the downstream task of hate speech, then there you see that the epochs that are early are performing better, and this was consistent across data sets. So this is for other data sets as well, and you can see that each of these data sets, the higher peak is towards early epoch. So this was kind of intriguing, and we did this experiment on different seed MLP seed and different classification and complexity. And as you can see in this table, that the results are like pretty standard in terms of checkpoint 2 and 3 giving the highest performance. So and this was valid across all data sets. So what our hypothesis here is that when most of these data sets were taken from Twitter. Hello, is there a question? Okay,
No,
so
I don't
as
think
I
so.
was saying, that most of these data sets were taken from Twitter, where the syntax and the semantics is not very well defined, and like you have in informal English. So what our hypothesis is that because the text is kind of noisy, and the earlier epochs of your pre-training are kind of still trying to differentiate the semantics, the syntax, and the noise. So maybe that somehow connects with most of the data sets that are also having that kind of linguistic pattern, and maybe that is the reason why this is happening. So this is something that, in future research, not just for hate speech tasks, but other NLP tasks also needs to be checked as to what extent different checkpoints impact the downstream performance. And what it also means is that apart from like how you have the glue benchmark, which is usually used at the end of your PLM, like once you have pre-trained your language model, just to like show whether it has actually whatever techniques you've used is actually doing well, you use a glue benchmark as a test test bed. What we need is somewhat similar to that, but in for intermediate validation as well. So you need somewhat like an intermediate glue benchmark that can be used throughout your training pipeline. And of course something similar for hate speech as well. Of course we don't have a standard hate speech validation data set, but like this is something that we as a community can try to work towards, like how do we perform intermediate validation within your pre-training and fine-tuning pipeline, especially within the pre-training pipeline. So this was like the major takeaway. And I think that this particular result may have implication in terms of like, can we build more cost-effective models now that we see that training them fully till all the epochs is not necessary. Then the third RQ that we studied within the pre-training domain focused on the pre-training data itself. So we know that BERT was released in 2018, 2019, around that time. And then you have every time a new variant of BERT was released, let's say when Roberta was released, or when now newer LLMs are released. So ChatGPT stores information up till 2021, 2022. So we know that when a newer model comes, whatever delta data set improvement it needed, it picked on that. So if I'm training a model from scratch today, then I will take all the information on the internet up till 2024. So there is always an increment in the data corpus that is used in pre-training. But is there any impact of this increase in the corpus, or so-called updated or more latest information in terms of like hate speech detection? So for this, we again relied on the Roberta variants that are released by the Hugging Face OLM project. So the OLM project, I don't think it's very active now, but when it came up, its aim was that we are going to release a language model in frequent intervals, so every 3-4 months, and whatever web corpus is added for that 3 months, we are going to use that as a new data to train the model on. So keeping all your training pipeline, just whatever the delta data is available new, they will add that to the training. So here we got hold of like 3 variants of Roberta. The first is the Roberta base itself from 2019, and then the other 2 were Roberta that were released in October 2022 and December 2022. And again, the general hypothesis will be, yes, as your pre-training data is increasing, it should learn newer information about hatefulness, about what's going on in the world, and that new information, new knowledge about hatefulness should help improve the performance for the data sets. But the results were quite contrary, especially for like data sets like Wasim, David, OLED. You see, for these data sets, the performance, even for Davidson, like the performance variation between base and the latest model is either 1 or 2 points, or it is negligible. So you don't have to worry about using newer models on these data sets. But again, Wasim and Davidson are really OLED. These are data sets that came around or before even Roberta base. So it means that whatever knowledge is stored in these data sets, it pretty much is covered within the base itself, and then newer models are not giving any extra information to help this. There were 2 data sets where the performance improvement was significant, like in Fonta and Hate Explain, where it improved almost by 25 points in Fonta. So we see that for some data sets, it is helpful. It can so our hypothesis here is that it can also depend on the complexity of the data set itself. So the more nuanced the data set, like Hate Explain had multiple annotations by multiple people, and it had target values associated with it. So the more nuanced the annotations are, the better learning can happen over time, but largely it doesn't matter. So that was like one observation that we had here. But the major takeaway here was that while you are while the gap, you're trying to fill the gap in the pre-training data for PLMs, we're not doing anything to fill this gap for the benchmarking data sets themselves. So you're saying that the PLM is trained on newer information, but your benchmark data sets are not keeping up with this new information. So this comparison is kind of like not very like well it's not very well balanced. Because you're already skewed in sense of the newness that PLMs are that the LLMs are able to carry. So what we as a hate speech community need is to be able to come up with some method where we can continuously keep on adding newer cultural sensitivity, newer information, and kind of collating that in some sort of a leaderboard. Let's say you have today we have like 100 hate speech data sets from different communities or different language, and we collate that in a leaderboard, and we make sure that when new hate speech data sets are released by people from other countries, that we kind of encourage them to add their data to the leaderboard, so that whenever a new PLM gets released, we can perform this benchmarking. Like how now for LLMs, we have that agent-based benchmarking as well. So, developing something around that line could be useful for hate speech literature, especially because there is a delta in terms of when the data, when major data sets, the famous data sets were released versus the newer models that you have. So that somewhat covers the question that we had in terms of the pre-training strategies. I'll now be talking about fine-tuning strategies. So here we focus on two questions. The first is, of course, performing these pre-training experiments with different checkpoints, different checkpoints that are released in terms of epochs or weights, or even newer incremental data sets. It's difficult. So, but what is easy to test, or what is more viable for most people is changes in the fine-tuning strategies. So the two fine-tuning strategies that we'll be talking about are the layer-wise freezing and the classification head. So in the first one, we want to see is there any pattern in terms of individual layer as well as group of layers that can impact your hate detection. So when we say freezing, it means that that particular layer is not set to trainable, and backpropagation will not update the weights for that. So it is not trainable. And when we say non-frozen, we mean that it is set to trainable. So in layer wise, what you can do is you can keep one layer frozen and train the rest of the layer, or vice versa. So as we know that BERT has like a set of encoder layer stacked on top of each other. So we are working with BERT base, which is 12 layers. So when I say about let's say testing layer one as frozen, what I'm doing is that I'm keeping this layer set to non-trainable. I'm training layers 2 to 12, and then you have your classification head at after 12th layer, and you are running your fine tuning on that. And when the backpropagation happens, layer one weights will not be updated. But if I'm keeping layer one as trainable and not using layer 12 to 2 to 12, what I effectively have is a BERT based model of only one layer, and my classification head would be somewhat attached. Like if you visualize, it is attached here at the end of the first layer, and when the backpropagation happens, it will only impact the weight of the first layer and not the other layer. So these are like some sort combination that you can run. Keep this layer frozen, keep this layer frozen, and you can also do this in terms of groups of layers. So how we define regions or group was that we took layers in terms of three consecutive batches. So you have 1, 2, 3 layer forming the first group. You have 3, 4, 5 forming the other group. So in batches of three consecutive this we form the layer. So we didn't do the windowing approach. So it's not like that after 1, 2, 3 you have 2, 3, 4. We didn't do that, but it was like after where the last group end, the next group will begin after that. So we did that grouping for group of layers. But as these experiments can be performed at single layer or a group of layers, so we did that. And what we see in terms of layer wise result is that, of course, depending on the layer that you have employed in your data set, so some of those layers will give you a very a high increase in performance, and it's significant for most of these. So this layer, this was performed on like the four BERT variants: BERT, BERT, HATE-BERT, and MBERT. So this slide doesn't include MBERT results because it had certain different observations. I'll be coming to that later. But in terms of BERT, BERT, and HATE-BERT, what we see general, the status quo, which says that the layer which is closer to your classification head will play a more significant role than, say, the initial layer in terms when you are fine tuning every layer. So we saw something similar, that the layers that are towards the classification head, even when you are performing this layer wise freezing, we see that those layers play a more important role, at least in 5 of the 7 data sets. So the trend is significant for 5 data sets. So which means that even when you are performing freezing of let's say a particular layer, that particular layer, even in frozen state, if is as good as your first layer not in frozen state. So this means that when you are performing fine tuning, as it is the status quo in NLP, you try to make sure that you fine tune your later layers more. So this was in line with existing literature, the trend that we saw. But we saw two more trends. One with respect to the MBERT model. So this is the result for MBERT. Here we saw that mostly the layers that were performing well are when we were fine tuning the middle set of layers. And the other observation was that because we are looking at English data sets and MBERT is a multilingual model, compared to BERT, the performance on MBERT was lower. So say, for example, here the maximum F1 obtained for Wasim is 0.793, but on BERT, the maximum F1 went up to 0.85 or 86, if I'm sorry, yeah, if I'm not wrong. So you see that there is a difference in performance in terms of what MBERT is giving versus BERT. So that was one observation. The other was that for MBERT, unlike other BERT variants, the middle set of layers seem to be playing a more important role. So our hypothesis here is that, and this was somewhat in line with another work that did this analysis for MBERT on monolingual German versus MBERT, where they were doing this for name entity recognition and POS tagging. So they also had similar observation. And the hypothesis here is that, in MBERT, you have uh, you are trying to generalize for all the languages. At the same time, you're trying to learn specific information for that particular language. So there's a trade-off between generalization and speciality, and somehow the middle set of layers are the ones where this is getting captured maximum, which is helping the specific language that you have. And that could be one of the reasons why between this trade-off across different layers, you see the middle set of layers capturing most of the information that is needed for your classification task. So this was an interesting observation, because even when we do employ MBERT for our multilingual data sets, we usually fine tune it in the similar manner as we do BERT, which is where we try to focus on fine tuning the later layer. What would be interesting is that you perform similar experiment, but you fine tune the middle set of layers. So that was one important takeaway that we had from this. And I just wanted to quickly show results for like group wise performance as well. So again, in terms of group wise, what we see is that the property whether a certain group of layers perform better or not depends more on the data set rather than the variation in the model. Of course, with MBERT, we did see that the middle regions are performing better. But in general, what you see is that the data set property, it's a property of the data set itself, how the different group of layers are performing. So this was again an interesting observation, that you cannot make a generalized observation ki, acha, for all hate speech data sets, you perform this sort of like freezing, unfreezing, and it will, go generalize. So that was important takeaway for us here. And as I said, like the takeaway here in terms of grouping was that, of course, in terms of performing it group wise is easier than doing it for a single layer because the number of experiments reduce. But more than that, what was the major takeaway was that it's more of a property of the data set. So similar data sets may have similar similar pattern, and we saw that in our paper itself. But mainly it is the data set dependent. The second, rather than being dependent on the underlying model. And the second observation, of course, is for the embed, where we say that if your data set itself is not multilingual in nature, if it's an English data set, it's better to go for a monolingual model. Or if, say, you have a data set in a particular language for which the monolingual BERT exists, then it is advised that you try experimenting with that as well and show the comparison between that monolingual BERT model that you have and the MBERT model. So you do a much fairer comparison, and maybe you will even see a higher performance on that monolingual model. So coming to the last argue, I'll quickly give an overview of the question about the impact of classification head. So of course, the hypothesis here is that the more complex the classification head is going to be, the higher the increase in performance. But we also know in general from literature or in deep learning that when you keep adding more layers, it doesn't necessarily mean that the performance keeps increasing by the same ratio, by the same proportion. So after a point, adding more layer doesn't have any effect. And we somewhat saw this where we see that going from a simple to medium leads to a high jump, but going from medium to complex, because our medium and complex are also very similar except for the dropout layer, we didn't see much difference. And in some cases, like we saw that a combination of simple plus XYZ variant of BERT is as good as that of medium plus ABC variant of BERT. So classification head plus the PLM themselves had a role to play here. So this is just an example on Dynabench, but I'll show this result for all. That, as I was saying, that going from simple to medium seems to be effective strategy, but going from medium to complex, like adding dropout or adding more complexity in terms of your model, in terms of your classification head, may not be that effective. Similar results obtained for other data sets as well. And as I was saying, that you look at the performance of MBERT versus BERT, and you see that MBERT's performance is not that good compared to other BERT variant. An interesting observation that we had was for the BERT tweet model. So usually when hate speech detection fine tuning is performed, people is if it's an English data set, then people show the results on BERT and hate BERT, but we hardly covered BERT tweet. But our like our results and our takeaway here is that it seems that BERT tweet is also giving competitive performance. This again goes back to the fact that most of the data sets in hate speech, at least till last 1.5 years, till last 1.5 years, they were collected mainly from Twitter. So having the knowledge of the Twitter linguistics will definitely help these data sets much, and it seems to be helping much more than any domain specific knowledge coming from Hitbird. So our takeaway here is that if you are showing your results on Hitbird, it is advised that you also show your results in terms of bird tweet. And again, it calls into question the extent of like domain specific models like Hitbot, like how useful are they in the long run, and how useful is MLP as a strategy to capture domain specificity? Is mass language modeling as a task enough for domain specific models? Do we need to look at some domain specific pre-training tasks? So it opens up the Pandora box of like how domain specific models should be built. And in concluding remarks, I'll just quickly give an recap of some of the major takeaways that we have. The first is, of course, as you saw in the initial experiments, that we were working with 25 checkpoints, 84 checkpoints. So for us to be able to perform this experiment on other LLMs or multilingual setting, you need those checkpoints to be released. So how can we better manage and maintain the intermediate checkpoints is one question for the NLP community that we have. And again, more analysis is needed on a variety of NLP tasks that are not covered in the glue to check about the role of like mbert versus a monolingual word that is available for that. And then, as I was saying, the role of like domain specific LLMs. So I think with this I can conclude my presentation, and we can open for questions.
Okay, thanks, Sarah, for this wonderful talk. So, if
Yeah.
anyone have any question, they can ask.
Hi, I would like to ask a few questions.
Yeah,
Yeah,
sure,
sure.
sure.
So can you please explain a bit about this macro F1 which you were showing in your charts?
Which slide? Like which one? Which macro
Like
F1
in
are you
at
talking about?
last in the last slides, the results
Okay.
that's macro F1 was on the y-axis. So I'm not aware of this macro F1. So can you please tell me a
So
bit about it?
like like you have your concept of like precision and recall, right? uh, you have accuracy as a metric that is usually used.
Yeah.
So accuracy
Mhm.
basically how many input you had and which of them were correctly classified. It's a binary one-to-one mapping. But what happens in case of skewed data set? So let me give you an overview in terms of hate speech. The data set labels are very skewed. So say if you in your data set you have 10 non-hate samples, then you have one hate sample against it. So the class balance is skewed. So what we need are metrics that can account for this class imbalance. Otherwise, in terms of accuracy, it can be 90% accurate, but that 90% accuracy is coming from labeling everything as non-hate. So we don't want that for skewed data set. So there you come up with metrics like F1 score and macro F1 score. So they make sure that your class weightage and class labels are accounted for, and these results are more balanced in terms of your class labels.
So while talking about class imbalance, so Cohen's kappa is also like some people suggest for using where
Yeah,
there's a
yeah.
class imbalance.
Yeah, so see, kappa and everything is good in terms of measuring your inter annotator agreement. That is like two people have annotated the data set. So you can think, yes, as an extension you can think that any hp classification task or any other task can uh, be a measure of annotation done by say the human and the model. So you can have that as a metric as well. But the standard practice is the F1 score. Kappa values are usually shown in terms of your annotation. So difference in annotation variability, like how correlated are the annotation. It goes in that direction.
Okay, so one last question. As you were mentioning, like this hate speech problem is there for quite some time now, but still we don't have any accepted or well accepted benchmark. So what do you think is the reason or why people are not addressing it?
So it's less an issue about not wanting to address and more of an issue of how can we address this. Because say if say the 20 people here in this talk decide that we are going to come up with a benchmark for hate speech in Hindi today. So the data that we will collect will focus on the topics that has happened in the past or that are currently happening. But what if there is a new event tomorrow? Or say today maybe in India religion and caste are two very strong points on which a lot of hate can be generated. What if tomorrow these don't become relevant, but some third other uh, uh, class of people become more vulnerable? Then how do you make sure that this delta change is updated? Now I'm just giving a very broad example, but if you look at it on a day to day basis or a cultural sensitivity basis, then these changes every few months, every few years. So how do we keep the benchmark itself updated? So there cannot be like one data set. So there is a line of work like hate check point hate check and multi-hate check and hate check for specific languages. So what they are trying to do is they're trying to build certain patterns in which hate speech is written, and try to generate sentences in that pattern, and kind of see that, okay, what if there is a sentence that has a hate term, let's say some abusive words, but it is not hateful in nature, like how in talking to our friends we sometimes use some abusive words, but we don't mean that as hate, right? So what about you have a sentence like that? It should be classified as non-hate. What if there is a sentence that contains that abusive term, but it is intended in a hateful manner? Then it should be classified as hate. So you have these different kind of variations that you can create. You have certain rules that you can use, and then use these rules to generate your hateful and non-hateful sentences, and check that against your model. But again, these rules, since the time they were created back in 2021 2022, so there was a lot of work in this, so they are now static. What if you want to add newer rules? How do you do that? When we talk about things like blue benchmark, your aim of how you class do name entity or how you do POS tagging, in English it has remained pretty much standard. But here in hate speech, that is not the case. So you need something that works in a continuously updated manner. So that's what I was saying, that even if you want a leaderboard, that leaderboard needs to be updated on a regular basis, and the community itself needs to make sure that any new paper or any new data set that comes, it gets added to that leaderboard pipeline, so that evaluations can be done across data sets. But there's no one benchmark that can happen. That's like a very intractable task for hate speech.
Thank you.
Okay, any further question? Okay, I think there is no further question. Okay, then let's thank Sarah again for this wonderful talk. And yeah, so thank you again, and we'll meet again next week.
Yeah.
Thank you. Bye.
Thank you for hosting. Thank you guys for joining. Thank you so much.